Rockets are some of the most complex machines humans have ever built. They're designed by engineers who understand fluid dynamics, thermodynamics, control theory, the works. So why do they keep exploding? The answer's simple. Rockets are just controlled bombs. Giant pressurized tubes of super cold, super flammable chemicals. They're held together by math, steel, and hope. If anything goes wrong, a sensor glitches, a pipe cracks, a seal stiffens, the whole thing can go up in smoke. And in rocketry, things go wrong a lot. Let's start with the basics. Rocket engines burn fuel and oxidizer in a combustion chamber to produce hot gas. That gas is forced out the nozzle, which pushes the rocket upward. Newton's third law. Action and reaction. Push down, go up. But managing that push is like juggling a chainsaw. The fuel is often cryogenic, stored at extremely low temperatures. The tanks are under massive pressure to keep the fuel moving, and all of it has to stay perfectly balanced. If pressure builds unevenly, explosion. If two chemicals mix too early, explosion. If a seal fails under stress, you get the idea. SpaceX's SN4 exploded during a routine test. No flight, no engines firing, just a failed detank valve and a little leaked methane. That's all it took. One spark, and the rocket vanished in a fireball. And not all failures are mechanical, some are digital. In 1996, the Ariane 5 rocket reused software from its slower predecessor, the Ariane 4. The code tried to convert a large velocity value into a smaller data type. It didn't fit. The computer crashed, the rocket lost control and self-destructed, all because of one line of code. In rocketry, even the math has to be airtight. Then there's vibration. When a rocket accelerates, its engines, fuel lines, and structure all start shaking. That shaking can hit a resonant frequency, like pushing a swing at just the right time. This is called pogo oscillation. It's violent, it's dangerous, and it nearly destroyed the Saturn V. The astronauts described it as brutal. Instruments blurred, their vision shook, the whole rocket flexed like a diving board. Engineers fixed it, eventually, with dampers and structural changes, but the first flights were terrifying. Even when everything seems to work, unseen forces can stack up and turn a smooth launch into a disaster. In rocketry, stability is never guaranteed. And sometimes, the engineers are right, but no one listens. In 1986, engineers warned that launching Challenger in cold weather could be dangerous. The O-rings and the solid rocket boosters were known to stiffen at low temperatures. They might not seal properly, but the launch went forward anyway. The O-rings failed. Hot gases escaped, breached the fuel tank, and the shuttle disintegrated 73 seconds into flight. 7 lives were lost. The physics didn't fail, the humans did. Rockets explode for all kinds of reasons: structural failure, combustion instability, bad code, ignored warnings. But each explosion teaches us something. Failures refine the system. Every leak, every crack, every detonation reveals a weak point to fix. We remember the disasters because they were loud, public, and tragic. But we also remember them because they made future flights safer. So yeah, rockets explode, but that's part of the process. If you like this breakdown, leave a like, drop your thoughts in the comments, and subscribe to Ignition Point.